Hello and welcome back. Today we will be looking at actually the beginning of section 1.2. We looked at the end of section 1.2 last time. And we're going to look at limits, and we're going to look at them sort of algebraically rather than with a picture. I do want to start out with a picture though to help remind us some of these basic limits here. So here I've got the limit as x approaches 2 of -1. And again, if we graph the function -1, it's just a constant function. Imagine it goes through point -1 down there. And we can see that no matter what point we choose, if we point x is equal to 2 out here, if we approach x is equal to -2 from the left and from the right, it doesn't really matter where it was we chose. This limit is still -1 because that's that height there. So with a constant function, it doesn't really matter where we're approaching, what x is approaching. The limit's always just going to be -1. Constant functions are pretty nice. The limit as x approaches 2 of x, well, the graph of x with just slope 1. This is pretty straightforward. And again, if I want to approach 2 here, so as x gets close to 2, either from the left or right, we can see that no matter what it is we're doing, we're always approaching 2. So the nice thing about this function, the limit of x is always going to be what it is you're approaching. If I plug in 2 in for x, yeah, if we're getting closer and closer to 2, x is getting closer to 2. It's the same thing. If x gets close to 2, x gets close to 2. And then this last one is where things maybe start to get a little bit more interesting. We've got x minus 1. So again, we've got a slope 1, but a y-intercept of -1. So then we'll go up like this, come down like this. And again, now we actually have to do a little bit of calculation. As we approach 2 from the left and right, we can see that we're up here, and as we approach 2, the height of our function is actually approaching 1, which quite looks like 2 minus 1. 2 from the x is approaching 2 minus 1. So it would be nice if I could just plug this 2 into here and get 1. And we'll essentially show by the end of this lesson, and then forever else in the rest of this class, that we can do just that. As long as our function is nice in here, we can just plug in our value and find the limit. So let's look at some algebraic properties of limits. The first observations that I want to make were some that I was talking about before. And the first one is that the limit of a constant function is that constant. So the limit as x approaches a of c is c. The limit, this function is a constant function, so it just goes straight left and right. It doesn't matter what x value we pick. We are always at the same height. So the limit is always just going to be that height. Nothing ever changes. This limit is always just going to be c. Okay, so this one is fairly straightforward. And then down here, the limit as x approaches a of x is a. And again, this is almost a tautology, just a statement that is true. A statement that basically says nothing. Like, the color blue is the color blue. I haven't really said anything, have I? As x approaches a, x approaches a. That's it. So this limit is kind of silly. When I was looking through the textbook, it gives names. It gives names to some of these observations. So this they called L1. This they didn't explicitly mention anywhere, so I've given it my own name, L1.5, because it feels like it should be the second thing on the list. So now that we've got so the limit of constant function and the limit of what's called the identity function, we can start expanding things now. So here, our next property that I'm just going to assert is true is that the limit of f of x to the nth power is equal to the entire limit of f of x all to the nth power. So So here it doesn't matter what number n is. So it could be to the first power, which would make this a little bit trivial. It could be that I'm taking the limit of f of x squared should be the square of the limit. I could also be raising this to a negative power, but we have to be careful here. If n is negative, then f of x, f of x needs to be positive. Or non-zero. Why? Well, if you take 1 divided by 0, we don't get a real number. So if we want this limit to exist, we better not be taking a limit and get 1 divided by 0. We have to be a little bit careful. And for instance, n could be 1/2. So I could take the square root of a function, and what I'm just going to get is the square root of the limit. So these are just some things to keep in mind, and we'll see some examples of this in a little bit. And then the next one is, again, more or less exactly what you'd expect. If you take the limit of a function plus another function, or a function minus another function, just take the limit of each of them individually and add those limits together, or subtract those limits. And again, in order for all this to make sense, the limit of f of x and the limit of g of x need to exist. So it's not as if I could take the limit of f of x to the nth power and just say, oh, this is just the entire limit raised to the nth power. If that limit doesn't exist in the first place, I can't take something that doesn't exist and raise it to the nth power. So it's good to keep this in the back of your mind, and I'll emphasize this in the next couple of examples. So let's find the limit of x squared minus 7 as x approaches 6. Well, first of all, I notice that I'm taking two functions and I'm subtracting them. So what I'll do is I'll write the limit as x approaches 6 of x squared minus 7. Well, provided that the limit of x squared exists and the limit of 7 exists, this is just going to be the limit as x approaches 6 of x squared minus the limit as x approaches 6 of 7. And this was this last property that we saw. This was because we can subtract the limits. Cool. So now we just need to show what the limit of x squared is and what the limit of 7 is. Well, the limit of 7, oh, that's pretty simple. The limit of 7, this is a constant function. It doesn't matter what we're approaching. If we have a constant function, the limit of that constant is always just that itself. And that was the first property that we saw. So now we need the limit of x squared, and again, I'm taking my function here and I'm squaring it. So this is actually going to be the limit of x as x approaches 6 squared. And this was the second property that we saw. Okay, so we had a 1.5 in there as well. And then now I can just take the limit as x approaches 6 of x. Well, that's just going to be 6. So we get 6 squared minus 7. And this is something that we can just simplify. So 6 squared is 36, minus 7 is going to be 29. And that's it. So we just used the properties of our limits. We used property 1.5 to simplify the limit as x approaches 6 of x. We used property 3 to say, oh, I've got the limit of two functions that are being subtracted. I'll just take the limit of both of them and subtract them. And then in here, we use some subtle ones. The limit of a constant function is just that constant. And the limit of something to a power is just that limit to a power. Is the limit of that function to that power. Okay, so let's look at this next one. The limit as x approaches 6 of 3x. So we're multiplying two functions, right? We're multiplying the function 3 and we're multiplying the function x. But if we come up here, none of our properties deal with multiplication, do they? This is the limit of a constant function. This is the limit of the identity function. This is the limit of something to a power. This is the limit of something being added together. But addition, this should work, right? We don't have multiplication, but we can be clever. The limit as x approaches 6 of 3x. What is 3x? This is just the limit as x approaches 6 of x plus x plus x. And there you go. So we can take the limit of x plus x plus x. So I haven't really used any properties of a limit right now. All I've done is I've rewritten 3x as x plus x plus x. So there's no I haven't used any properties of limits. I've just used some algebra here. Now I'll use some properties of limits. The limit of x plus the limit of x plus the limit of x. So here I've split up my addition that was inside of the limit to addition that's now outside of the limit. So I think that was property 3. And then the limit as x approaches 6 of x, well, that's just 6. This is just 6, and this is just 6. So we do get 18. And then that was the property 1.5 that we saw. So far, all we've done is see that, yeah, we can take limits fairly simply with a couple of these properties. It would be nice if I could multiply limits as well, and it turns out we can. So we've got another 2 more properties that'll go through. The first one is exactly what we were just discussing. The limit as x approaches a of 2 functions being multiplied together is just their limits being multiplied together. So there's nothing crazy going on there. But if we can multiply, we should be able to divide, right? So again, if I take the limit of f divided by g, I should get the limit of f divided by the limit of g. But again, I don't want to divide by 0, so I have to be a bit careful here. Now, I've listed this as a property. It turns out I don't need to list this as a property because I can get here using my other properties. So let's prove that L5 works using some of our other properties. So let's say that we want to find the limit as x approaches a of f of x divided by g of x. The first thing that I'm going to do is I'm going to use some algebra. I'm not going to use a property of a limit yet. F of x divided by g of x, this is the same thing as f of x times g of x to the negative first power. Because if I raise something to the negative first power, I'm taking the reciprocal of it. So g of x to the negative first power, that's just 1 over g of x. And f times 1 over g of x, that's this. So I've turned division into multiplication with an exponent. And we know how to do multiplication, and we know how to deal with exponents. So this is going to be the limit as x approaches a of f of x times the limit as x approaches a of g of x. And again, with this negative 1 power in there, going to raise it to the negative first power, and we get exactly what we want. I'm probably not going to have time to write this down. So we can get properties property 5 without using, without just stating it. I can prove it.